Cool. I think we can get started for the lecture since it's 8:35. So today we'll be covering an introduction to GAN, what are GANs, what are the applications of GAN, and how do you train GAN. So
I think the mic is not working.
No, really?
No. You want to try testing? Testing. Do you need? I'm not sure if we can ask them to turn up the volume or something. Try plugging into the title. Sure.
I don't know. Really?
They're not projecting in the room.
No. I think I think the voice is actually quite
Let me
low.
see. I might turn up the gain a little bit on
All right.
those. Not the other one.
Oh, another one. Oh boy.
Yeah. I know. Here. Try it now. Okay,
Test.
Try right there.
Okay.
It's probably hard with the mask on too.
Yeah.
Try it now.
Test.
Oh yeah.
There you go. Yeah.
Cool. Oh boy. Okay. So this is like a code from Professor Yan that he thinks that GANs are one of the most amazing thing, in fact, the most amazing thing in the last 10 years in deep learning. So you guys might have already heard about like DFake, like how people are using GANs to train the DFake, like switching faces from one person's body to another person's body. Let's see an example of how this happens.
Just when you think you've reviewed every ergonomic keyboard on the planet, a new company with a name like Truly Ergonomic launches something like this, the Cleave keyboard. Apparently the
What?
No, I think
most
it's
comfortable.
not playing on the other screen. Let me just. You have to exit out. Yeah.
Yeah, that's
That's
fine, right?
But honestly, there's lots of
Okay.
comfortable keyboards out there. For me, it's about meeting that minimum ergonomic threshold while also having a decent layout that doesn't suck to use. Looking at the box, it says it uses optical switches, and the word new here to me implies that they might be proprietary. Comes with a combined key cap puller and key switch puller.
Yeah, you're right.
I think we can just stop it because I think there's
Yeah,
no
that's
comparison
fine.
part.
Cool.
Yeah, you just go back
Okay.
and.
So the video you just saw, it wasn't the real person. It was the face was swapped by another person's, and he was actually they used this face on the right, the voice from the right, and then swapped another person's face into his body. So this is what you do with GANs. And in this lecture, we'll be talking about how you train GAN, what are the motivations of GAN. So these are the content for this lecture. We'll go through what are generative models, difference between GANs and VAEs, and introduction and theory about GANs. So why do we need to train a generative model? I mean, we have models which can actually, what we have been training in different homeworks that, mapping, given X input, we are mapping it to a classification model like you did in your first homework, second homework for images, and so on. So why do we really need generative models? Well, maybe you want to generate new images. Maybe you want to generate new recordings, and maybe you want to generate some text given an input. So these are the things like you really can do with generative models. And even in the last few lectures, you saw VAEs, how you can actually generate new images, given input image. And that's something similar which GANs also do, but in a different manner. So these are like the this was the original paper from Ian Goodfellow, and you can see that the images on the right in each section are the original ground truth, and all the other images are generated from GAN. So you can see that the GANs are, the images might be blurry, but it's actually creating the actual image. It's trying to create images which is similar to the original training set. And now you can see here how GANs progress throughout the time, like when the first paper was published in 2014. The image you can see is that it's kind of blurry, the resolution is not very great, but as time progresses with more and more GPUs and more and more good image resolution, you can actually get a better image. Like you can see in the 2018 example, the resolution of the image is very great as compared to the resolution in 2014. So this is the StarGAN paper. It was published in 2018, which was trained on a celebrity data set. I don't know if you guys have heard about it, but it's basically a data set of faces of celebrities. And you can see in that, given an input image on the left-hand side, the GAN is trying to do image translation, taking an example and then changing the hair of the person, even changing the gender, age, and the skin color of the person. And this is an example, a really good example of image-to-image translation. Given an image, you can change the appearance of the image. This is also very something similar. Let's say, for example, you take a horse and then you do image translation to that. The horse has stripes, so now it looks like a horse, but it can have zebra stripes as well. So those are the examples which you can generate. Those are the images you can generate from GAN. And you can also see that you can actually change the facial expression of the person as well. In the right-hand side, you can see that, given an image, you can make the person angry, happy, or fearful, like that. And this is also another from another paper. The resolution you see is 1024 by 1024. It's really good. The resolution is really good. These are the people who don't really exist. So these faces are actually not from a real person. It's actually generated from a GAN. And even you can do that as well. You see, it's not just about the images. You can actually get high resolution output, not just from face, but almost everything. You just pass in the input data, train a GAN, and then it produces high-quality images. So the original paper, I think, it was 28 by 28 resolution, I think. But as time progresses, the resolution is really great. You get very high resolution. So we saw that what a generative model can do. So now let's look at what does it mean by having, how does a generative model differentiates with a discriminative model. So in a discriminative model, what we are trying to learn is we are mapping, given an input x, to an output y. and we are learning the conditional distribution, which is given an input x, you are trying to predict what could be y. But in a generative model, what you're trying to do is you are trying to learn the joint distribution, meaning you're learning the distribution of both x and y together. So when you're learning a joint distribution, what you really get is that you can now just not just go from x to y, but you can also go from y to x. So let's say, for example, for your homework 2, which you did like given input of images, you are trying to predict what kind of class is there. But when you are learning a joint distribution, what you can say, okay, I have mapped input x to y, but now I'm doing joint distribution, so I can now map from y to x as well. So you can, if you train a joint distribution, you can say generate a class y for me. So when you say generate a y class, your model will produce an image. So that's what generative model does. Do you guys have any question about conditional distribution or joint distribution? Nope. Cool. So it's a whole thing that the discriminative model learns the conditional probability. It learns the boundary between the classes in case what kind of images given an input x, you are trying to predict, okay, this image belongs to a particular class. And in your generative model, it's basically learning the actual probability distribution between your x and y. So the discriminative model, it is only helpful if you're just doing some kind of classification task. But when you learn the joint probability, you can actually not just do the classification task, but can also do generative stuff. Like you can generate different data. So that's the whole that's the benefit of generative model. And these are like the examples of what kind of generative models, logistic regression, SVMs. They are a discriminative model, and then naive Vaes, Gaussian mixture model, and VAEs, GANs. These are generative model in which you are trying to learn the probability distribution. So you have to look at when you train a discriminative model, it's quite easy. You just have to input an image, and you just have to classify something or do any kind of small regression stuff. But when you are training a generative model, you have to get the deeper understanding of the distribution of the model. And then only you can actually generate new images. That's why it's hard to train generative model when we compare it to the discriminative model. So explicit and implicit model. I think, can you release a poll? Oh, wait, after this slide.
Okay.
After this slide. So explicit distribution of the model is basically like you are, making an assumption that input data the input data set belong to a particular distribution. Let's say, for example, you may be assuming that VAE or NA model is normally distributed. But in case of implicit model, you don't really know the distribution of the data set. So you are training the model to learn that distribution.
I think one correction is that I think the explicit distribution model, we're actually learning the distribution, whereas the implicit distribution model, we are not explicitly learning the distribution.
Yeah.
So
Release it,
we
Paul.
are assuming, but it's whether we are learning. It's not.
Sorry?
It's whether we are whether we are learning the distribution, not whether we are assuming that the X has any distribution.
Which one?
I mean, the first explicit one.
Yeah, in explicit is basically like you're saying that your data set follows or some kind of distribution, and you're learning the parameters of the distribution. Yeah, Paul.
Let me just open the post.
Have you saved it?
Yeah, all right. So transpose.
Paul, what?
Is it?
Oh,
Okay,
it's-
it's that, yeah.
Wait. 8090. What?
Did you, what is the configuration of the phone?
People can see, right?
No, okay, entire class. Yeah, submit. All right, I think pool 1 should be released now.
Yeah, I think we should close the poll now. So the question was, which of these are explicit generative model? So like I said before, that in explicit, you're doing some kind of assumption, and you're learning the parameters of the particular distribution. So you might have remembered that in VAEs, we are assuming like the data set follows a normal distribution, and you're trying to learn that distribution. But in case of GANs, you are not making any kind of assumptions. So it's not an explicit generative model. It's actually an implicit model where you're trying to learn the actual distribution of the data set. So the answer for the polls are VAEs and Bayesian networks. GAN is actually an implicit generative model. And for RNNs, it's not a generative model if we are just considering RNNs. So okay. So in VAEs, what we are basically trying to do is that we have this encoder-decoder model, and in encoder we are trying to learn, going from the input data to a latent space, and then generating the actual data from the given latent space. So we are basically trying to learn this latent space Z. This is the whole idea of VAEs. But how does a VAE compares to a GAN? Well, basically in VAEs we are using this KL divergence between the learned distribution and the actual distribution of the data. But in GANs, the loss function is actually different. It's Jensen-Shannon diversion, which you'll learn in today's class. Next thing is to minimize the bound on divergence between generated distribution and target distribution. So when you are when you are training a VAE and you are doing a divergence between the learned distribution and the target distribution, you get to a point that you are basically trying to limit this bound, which is bound between the actual distribution and the trained distribution. But in VAE, in GANs, it's actually like you are minimizing the divergence between the learned distribution and the target distribution. It's just that in VAEs you are minimizing the bound between the two distribution, and in GANs it's you are minimizing the divergence between the two distribution. So VAEs, like for when you are doing some kind of this assumption and trying to learn distribution based on that, the whole training is actually simpler. You might get to global you get to a global optimization. You can get global minimum because you know this distribution and you are just trying to learn that distribution, parameters of that distribution. But when you are trying to learn the actual distribution of the data set, in case of GANs, you don't really know where the global minimum is. So this optimization is actually difficult. And so that's why we come to the last point, that the results in VAEs are blurry. Can anyone explain, like, why do you think like the results from VAEs will be blurry? Sorry? L2 loss, yeah.
Using that loss, you just got a blurry result.
Anyone else maybe want to try? Well, think of go back to VAEs and think like what exactly they are trying to do. You have this input data set, and you are trying to learn, you are taking that data set and projecting it to latent space. So when you learn from that latent space, there is a loss of information, and you are trying to reconstruct the image, the input data from that latent space with your decoder. So that's something like when you go to the latent space, you lose some kind of information, and that's why the results get blurry. But when you learn the actual distribution, let's say in this what GANs actually do, the results will be sharper. The images which you'll generate, or recordings which you'll generate, will be crisp, and that's why you saw the really great results from GANs. But because you are trying to learn this actual distribution, this optimization gets really difficult, and that's why the training GAN can be difficult. You might not actually get to the global optimization. So this brings us to the introduction of GAN, like how to what are the components of GAN and how do you actually train the GAN. So GAN stands for Generative Adversarial Networks, in which generative is you're generating, given an input X, you're trying to generate you're learning that distribution of the data and trying to generate given that input distribution. So that's what even VAEs do, and that's why VAEs are a generative network. And this is the VAE model with encoder and decoder. So adversarial is because in GANs, you are trying to train two networks. One is the generator, and one is the discriminator. So these two networks are trying to compete with each other, and they are learning from the loss of the other networks and trying to learn from that. So in GANs, we have generator and a discriminator. A discriminator learns from the mistake of a generator, and the generator learns from the mistake of the discriminator. So these are acting as an adversary to both of these each other, and that's why it's called generative adversarial networks and networks. So the whole goal of training a GAN is generate from an unlabeled distribution. So what are the components? You have the input distribution, or you have the input with some distribution. The input follows some distribution. You pass it to the generator, and it trains the data. It generates the data. So you can initialize your generator with something random. So in your first few epochs, the generator will generate some noisy data. Then your generated data is basically passed to the discriminator. And the whole idea of discriminator is that it's trying to learn that given an image, it's predicting that, let's say, for example, given an image, it's trying to predict that is the given image a fake image or a real image. So by fake, I mean to say generated image. Is it coming from the generator or the actual training set? So when the image is coming from the generator, it's called fake image. And when we pass an actual image from the training set, it's called a real image. You pass the generated data and the real data, and the idea of discriminator is basically to predict that is it a real image or a fake image. So what kind of model is the discriminator? If it only has one task to do. Sorry? Yeah, exactly. So discriminator is basically a binary classifier. You can take any neural network to train the discriminator, and it's actually a binary classifier for just predicting real or fake. So this is the whole training of GAN looks like. In the initial few steps, the generator will create some kind of noise, random noise, which might not even look like a real image. It will mostly be noise. But then that's why we have discriminator, which acts as a loss function to the generator, so that once I have passed the generator and the training data to the discriminator, and if the discriminator actually spots that given an image, it's generated from the generator or it's an actual image. And when the discriminator gets it right, it actually acts as a penalty to the generator. So now the generator has to improve so as to fool the discriminator, so that the discriminator can't distinguish between a generated image and a real image. So this is like a zero-sum game. Both are trying to beat each other, and that's how they actually learn. And yeah, so we know that there are two networks in GAN. Which one do you guys think we should train first? Should it be the generator or the discriminator?
Discriminator.
Why?
I think we should have the capability to discriminate from the real image and the fake image, and we can use it as a guidance for the generator to generate a realistic image. That's my thought.
Yeah, that's correct. So the discriminator is actually, like I mentioned, it's acting as a loss function. So you are propagating that loss to train the generator. And the whole idea in GAN training is that you are basically you only mostly want to train the generator as good as possible, so that it can create better images or better data. But with what I should train the discriminator? Should I just randomly pass randomly create some kind of noise for the discriminator to learn, or pass in the input image. Well, what you basically do is, initialize the generator and make it to generate any kind of data. Like I mentioned, that it might even be noise. So what you basically do is just pass any generated data to the discriminator, and initially the discriminator will be very good at it, because during the initial few steps, the generator is basically or mostly producing noise. So the discriminator can learn between an image or a noise. So you train with that, and then you propagate with the response from the discriminator to the generator. And then you basically train the generator from the output of the discriminator. So the training objective of training a generator is that you generate some image, and pass the generated image to the discriminator, and if it flags as fake, then the generator will have to improve so that it can produce better image which looks like the images from the actual data, and it tries to learn as good as it can and matches the actual distribution of the input data. So this is the first step of training in GAN. You train the discriminator, initializing the generator with something. You train the discriminator. Then step 2 is basically you train the generator to be the discriminator. And then this is like a feedback loop. Both are training each other. Their response is training the other network. So if the discriminator is not really good, then the generator is actually getting better and better. Once the generator learns the actual distribution, then even the discriminator tries to identify or classify if it's a real image or a fake image. And then you get to a point that the generator can easily fool the discriminator. Initially, the discriminator is actually better at its job, because during the initial phase, it's mostly noise. But then as you train the GAN for many epochs, and the generator gets better and better, and then that's where you plan to stop the training. But as you might see in the next lecture, why this won't really work. Because let's say, for example, you are trying to train a kid with some image from 1 to 10 or something. So the kid can actually, is able to identify numbers like, say, 2, 3, 4, 5, and 8, 9. But if the kid is not if the kid is not able to distinguish between 1 or a 7, then it can actually make the discriminator better, because now it knows, like, okay, so the generator, when the generator generates 1 and 7, it knows that the discriminator is not able to distinguish between 1 and 7. So what the generator does, now it knows that the discriminator is being fooled at some images. In this example are 1 and 7. So the generator will now generate images for just 1 and 7, because it's good at that. When it's generating those numbers, it's easily fooling the discriminator. And this is actually a problem which you'll actually see in the next lecture. And this is how you actually do and then it's a training loop which recursively train the generator, discriminator, and that's it. So now we'll go to the theory part, which Z will cover. Board.
Yeah, just put it on my pocket. So yeah, can you hear me? Yeah, I guess it's working. All right, so now let's get to the exciting part of our GAN, which is the theory. Well, but I mean, it may not be as exciting, but well, it's definitely more intuitive than you think it is. It's, at least for the original GAN. So well, just to recap, GAN was introduced in 2014. The goal is to model the distribution of training data, and we're using a pair of models acting as adversaries. And so the generator learns the P of X conditional on Z, which means it's producing realistic looking data X from a latent distribution Z. So what is Z? Well, in the original GAN, or in a few of the GANs generating images like star GAN, Z is just sampled from a known prior, such as a Gaussian prior, right? We can just sample from 0 mean and 1 variance Gaussian. But I think recently there have been GAN models that is trained to perform, well, I guess a bit more meaningful tasks. So the input to the generator can actually be the input of the model that you want to train. For example, if you want to train a speech recognition model, your input would actually be processed speech segments, so that the generator would be able to produce phonemes for speech recognition. Yeah. So the third point, map a simple known distribution to a complicated data distribution. I think that only applies to the first kind of Z in general. Yeah, I would say this. So of course, the goal of the generator is to generate a distribution that matches the true data distribution. And the discriminator is trained to tell the difference between the real and generated data, as we just mentioned. And you can think of, as Manish has mentioned, discriminator can be think of as a loss function or criterion, right? Because if you look at the training, if you look at the diagram that was shown in the previous slide, we have a generator here that gets connected to a discriminator, which then gives us a loss function, which is 0, 1 loss. So if you want to backpropagate a gradient, the gradient of the generator actually comes from the discriminator. So that's why the discriminator can be think of as a loss function for the generator. And it's actually effectively thrown away after the generator is trained. So in the face generation, well, once you train the generator, you simply generate a random latent vector, and the generator will produce an image. You don't need this discriminator anymore. Right, so let's look at the original GAN formulation. As Manish mentioned, is a zero-sum game, so it's a minimax game. So the generator wants to maximize the chance that it folds the discriminator, while discriminator wants to, well, I would say, I think in this formulation, the discriminator wants to maximize the chance that it can discriminate between the fake and real images, while generator wants to minimize the chance that discriminator can do so. So we can see that the discriminator wants to identify dx as 1. So you want to identify real images as 1 and fake images as 0, right? So GZ comes from the generator. And the generator simply wants the DGZ to become 1, right? Now let's just see how do we optimize the discriminator for, let's say, one data point. So we have the original formula from the first page, and we rewrite the expectation into a integral form, right? So we basically integrate over all possible x. And let's just first look at one particular x and see how do we optimize it. So that's why we can just take. So that means we can just take the middle part of the equation. And so how do you optimize how do you find the optimal solution to let's say a convex function? I think the answer is on the slide. You take the first order derivative and set it to 0, right? So you take the first order derivative of this over dx and set it to 0. So you move move one of the term to the right-hand side of the equation. You multiply in this way, and you get the formula here. Then we simplify it. After simplification, we get this formula. So dx is pdx over pgx plus pdx. Right. So let's look at the two cases, two simple and extreme cases. So first, case one is a bad generator. So there's no way the output of the generator looks like my actual data. So how would what value would the discriminator output in this case? So let's just say that the discriminator says, the x comes from the actual distribution, data distribution is 0. The probability for x coming from the generated distribution is 1. And so if we apply substitute these two numbers into the formula, we get 0. So essentially, the discriminator will be able to tell precisely that the generator is bad. In the second case, the generator is good. That means I cannot tell the difference between the generated distribution and the training data distribution. So in this case, both PD and PG will become 1. Essentially, there's no way you can tell whether the x come from the actual distribution or the generated distribution. Well, that is just PD, this is just an extreme case. I think I wrote PDF there, but obviously if your PDF won't really be 1. But it's just some number that you can have a concrete understanding. Essentially, instead of 1, you can think of this as the x coming. The probability of x coming from either distribution is very similar. In this case, your dx will output 0.5. So, and that is, a stationary point that we'll talk about later. Yeah. So now that we looked at the optimal discriminator. Okay, by the way, any questions? Right, if not, all right, let's continue on the optimal generator. So recall we still have the original minimax objective. And let's try to minimize the formula here. So we can simply rewrite dx into, using the previous formula, right? We substitute that into both dx, And after simplification, we get this formula. And this formula turns out to be, well, two times the Jensen-Shannon divergence minus log 4. So what is Jensen-Shannon divergence? All right, so Jensen-Shannon divergence is basically reusing the KL divergence, but instead of comparing the two distributions directly, we find an average of the distribution in a way. Yeah. And we used KL divergence to compare the difference between each of the distribution that I have with my average distribution. So if you recall, if you don't recall the formula for KL divergence, it's right here on the right-hand side of the screen. So what's so good about JSD as compared to KLD? As it turns out, JSD is symmetrical. I think it's very easy to see from the formula that if you switch the order between PD and PG, the result will not change at all. However, KLD in the vanilla version is non-symmetrical in the function. Well, of course, you can make KL divergence symmetrical by just adding a term here with PG and PD swapped. So that makes the KL divergence, well, this is a variant of KL divergence that is symmetrical. However, the second property is also important. So KL divergence has no upper bound. It's lower bounded by 0, but there's no upper bound. However, there's a proof saying that the Jensen-Shannon divergence is actually bounded between 0 and log 2. So depending on the base of the logarithm that you choose, it can be 1 or it can be, well, log of 2, right? But essentially, it's a nice bound. What's significant about this is, imagine you have a really bad generator that generates a data that looks nothing like my actual data distribution. So if these two distributions are too far away, your KL divergence will actually become, may approach infinity. In this case, it's very difficult for you to tell, but well, how close this distribution actually is to, sorry, how close the generated distribution actually is to my actual data distribution, right? Yeah, so this, because both are two, if there are two kinds of generated distribution, and both are quite far away, it's not easy to quantify how far away they are. But Jensen-Shannon divergence allows since it's bounded, it's a better way of calculating or quantifying the difference between the two distributions, which is important because for GANs, we are actually trying to minimize this. Right, so if we look at the formula, the formula for optimal generator from the previous slide, so let's see how we arrive at the two times of Jensen-Shannon divergence. Well, it's actually quite simple. So we have 1/2 over here. That means I just need to take a factor of 2 outside so that I have 1/2 on the inside. And to match the KL divergence, so KL divergence is a formula over here. To match the KL divergence, I essentially need to replace PDX with my MX, which means I will have an extra factor of 2 on the numerator. That means I also have to divide by 2 outside. And by logarithmic rule, you can pull out the division of log 2 into minus log 2. So then you will get 2 times the JSD minus 2 times log 2. Oops. Yeah, which you put it in as exponent, you get log 4. So the optimal generator will simply minimize the Jensen-Shannon divergence between the real and generated distribution. And in other words, make the two distributions similar. Right, I think it's time for a second poll. Can you guys help release it? That's okay. All right. Poll 2. Well, 1889. All right, I think we have, yeah. Oh, looks like still going. Right. Not sure why it's decreasing sometimes. We don't allow revolts, so interesting. All right, I think we can close the poll. We should have enough time. Right, I think the answer is that it's B and C. So as we mentioned, discriminator should output 0.5 if the generator is good. And the 2 and 3 are obviously what is covered in the lecture. And for 0.4 of option D, obviously the input to the generator doesn't have to be sampled from a Gaussian distribution. That is the original GAN, but well, there are more variants of it now. All right, so this is a min-max switch to stationary point. So we just say, as we discussed before, if the generator data exactly matches the real data, the discriminator would output 0.5 for all the inputs. And if the discriminator output is 0.5, the gradient for the generator would be flat. Essentially, the generator would not be able to learn. But at the same time, it doesn't need to learn anymore. I mean, it's already good enough. The stationary point doesn't have to be stable, because as we know about the gradient descent-based optimization is not exact. So the generator may overshoot or oscillate around the optimum. And actually, the second point is interesting, that a discriminator, although the discriminator, ideal discriminator, learns the Jensen-Shannon divergence, the actual discriminator that we built would be actually more complex. So we actually cover that in the later slides. And a discriminator with unlimited capability can still assign an arbitrarily large distance between two similar distributions if the discriminator is very, very good. Yeah, so the stationary point itself may not actually be stable. And the generator and discriminator needs to be trained simultaneously. I think we have known that from the first part of the lecture. So if the discriminator is undertrained, it provides suboptimal feedback to the generator. And if the discriminator is overtrained, then there's no local feedback for marginal improvement. That means if the discriminator is so good that it can identify everything that the generator generates as fake, the generator will not be able to learn anything useful out of the loss function, the loss of from the discriminator. So that's why we always need an iterative process where we train the discriminator and generator simultaneously. And the objective is, of course, the minimax game. Well, GAN can be very sensitive to hyperparameters. So depending on the parameters of your choice, it may succeed in training, or it may just fail and generate noise, unfortunately. So yeah, that's why, tuning the hyperparameters is quite important. For example, for homework 5, I think if anyone of you is doing homework 5, you realize it's quite difficult to train the GAN. Yeah. There are many variations of GAN that attempts to make the stationary points more stable. So here are some of it. For example, this is the picture A shows this. I think these are just the gradient descent paths during the optimization process. So for standard GAN, it looks like sometimes it does not go to optimal at all. It simply oscillates a big circle around the optimal. So WGAN tries to improve this by using a different loss function, the Wasserstein distance, which will be covered in the second lecture, as well as using a trick called weight clipping. So that's why you have this shaded region here, because the weights are just basically we do not allow the weights to go into that region. So you physically limit the circle. And then another formulation proposed a WGAN GP, which is gradient penalty. So after gradient penalty, you do not need to do any hard clipping, but the circle is smaller. So you can reach a better optimum. Of course, I think in the later few cases, it actually got better using gradient penalty, instance noise. I guess this gradient penalty comes from uses a different GAN formulation. And to be honest, I tried to search for this CR, but I couldn't find what this means. So if you know what CR means, let me know. Yeah. But yeah, essentially there are multiple ways to make the GAN training more stable. But there's not a single solution that just works. And you probably have to improvise. You have to apply different tricks for different kinds of GANs to see if it works. So here's an interesting thing, a concept about perceptual loss. So previously we mentioned that GAN can generate sharper images than VAE, and we actually can see that. And why is the case? I think I heard a lot of I heard a lot of people saying that because the VAE uses a reconstruction process that makes the image less sharp as compared to GAN. However, if you look at the GAN architecture, it would also use reconstruction because the latent vector Z would definitely be smaller than the resulting image that you get. So for example, in the celebrity GAN, so I think star GAN, I think the input is 100 by 1 latent vector, whereas the output is a 64 by 64 images. So the key difference, I believe, is in the concept of perceptual loss. So as I've written here, and although an idealized discriminator calculates JST, a real discriminator calculates something that's more complex. For example, if your discriminator uses a convolutional neural network, then it's somewhat shifting variant, right? So this is not just a simple JST. And if you look at VAEs, so VAE's reconstruction loss is strictly a pixel-wise loss function. It can be a mean squared error or L2 loss, or it can be a binary cross-entropy loss, depending on the exact formulation. However, the loss function is more primitive in VAE. And whereas the discriminator can learn a better, well, how do I describe it? So as I mentioned, it can learn a better loss function that either better gauges the similarity from a human's perspective, or it has more properties than just a simple L2 loss. So that's the key reason that the GAN is able to generate sharper images. So to conclude the theory portion of GANs, there's the good, the bad, and the ugly. The good GAN can do wonders, but the bad GAN has stability issues and theoretical questions. And we need many ugly or ad hoc tricks and modifications, as I've shown before, to get the GAN to train and work properly. Right. Any questions? All right.
So what is a perceptual loss? I still have no idea.
Oh, okay. I think the students asked what is a perceptual loss. I think we're just saying that the discriminator loss is something that's more complex than just a L2 loss. So perceptual means, I think the explanation, well, my understanding of perceptual is that it's approximating how human thinks whether this is good or bad. But of course, the discriminator may not learn the exact loss function that we use to judge an image, but it will be something that's a bit more complex and it's closer to how we judge the image. Like I mentioned, VAE uses L2 loss, and that's a pixel-wise loss. Whereas while it is easy to optimize and train, it's difficult. It may not represent how we think two images are similar, right? And let's think of a simple example. Yeah, let's just look at a shift invariant case. Let's say you want to generate images with flowers, and since the training data has images of flowers on different portions of the image, the discriminator that uses a CNN may be able to pick up the fact that the flowers are on different parts of the image, and not penalize the discriminator, sorry, not penalize the generator for generating, let's say, a flower on this side of image versus a flower that's here, right? Yeah. However, if you use a simple pixel-wise loss, you see that these two images are not the same, right? Oops. And therefore, your loss, the VAE's loss function will actually will actually penalize the generator or the decoder for decoding an image that has a flower on a different position than the one that's in the training data. And I think that's why we say the discriminator can be thought of as a perceptual loss.
So do you mean that we do not have a specific form for the perceptual loss, right?
No, we do not have a specific form for the perceptual loss. Yeah,
Okay,
it's just that the discriminator in practice is better at it. Oh, yeah.
But we are still using the log loss for training, right? The objective is still the log dx plus log 1 minus p.
You mean the KL divergence or Jensen-Shannon divergence? Yeah, correct. Yeah, we're still using. Oh no, wait. I think you are saying the discriminator loss, right? Which is the binary classification loss. Yeah. So that is that. Yeah, that will actually be a KLD. Yes.
Where does this perceptual loss?
Okay. Oh, I see. So recall that in the very early slides of the theory part, we actually said that the discriminator can be think of as a loss function for the generator. Yeah, because your generator takes a latent image, sorry, a latent vector, goes to the generator, it outputs an image that gets passed into a discriminator. Maybe let me just put it down here. So you also have an actual data, well, or let's say training data, and you output 0 or 1. So the binary classification is loss is this part, right? However, in order to train the generator, the gradient has to flow through the discriminator. So your gradient will actually flow back to the generator for the generator to be trained. So in this case, you can actually think of this part. If you treat this part as a black box, maybe let me use a different color. Right. If you treat this part as a black box, then and treat the generator as whatever model that I want. Let's say in a supervised supervised learning, you are just learning. You build a model to learn some objective, right? And the generator is that model that you built. And this black box or the green box is a loss function that tells your model how good or how bad it is doing, right? So what I'm saying is that the discriminator can be think of as a perceptual loss function. Any other questions?
So if we use the idea of perceptual loss in the VAE, is it possible to improve its capability to generate realistic images?
Yes. In fact, you'll see papers that sticks VAEs. I think sticks GANs to the end of the VAE. Yeah, but as you can see from all the previous slides, the perceptual loss needs to be learned, right? So in regular VAE, you are not learning the loss function. Yeah. Oh, thanks. Oh, that's bad. That's just the live stream mic. So I guess. Okay. Sure. So. Where was the mic lost?
No, I mean, students are in MediaTek.
Yeah. Right. I mean, I just wonder how long was the mic out? Huh? Okay. No, I think it's just because the mic was on the floor. So. Yeah. It's not picking up my voice. Let me see. So should I repeat the last part of my presentation. All right. Okay, maybe let me just clarify this part, the perceptual loss again. I think the rest of the last section of this lecture will be pretty easy. So for perceptual loss, it is that because this is the GAN data flow diagram, essentially. So so if you treat the generator as whatever model that we want to learn, well, similar to a supervised model, then the discriminator plus the 0, 1 loss will be our the loss function for the generator. Because the gradient, if you look at the gradient flow will go from the 0, 1 loss, the binary classification loss, from the to the discriminator, and then from the discriminator back to the generator. So this whole green box can be think of as a loss function. And this loss function is ideally better than a regular L2 loss that's using VAE. So it could be it could better approximate how we judge the images. So that's why we call this that's why we can think of the discriminator as a perceptual loss function. All right. So now let's go back. Now let's look at the last part of our of this lecture, which is GAN evaluation. So some tasks have clearly defined metrics for evaluation. Like I mentioned, unsupervised speech recognition has, well, I think for homework 5 is the phone name at a distance. I feel that the reason is because these kinds of tasks can also be trained in a supervised fashion. So as I mentioned, as I noted here, a generator equivalent model can be trained in a supervised manner. In other tasks, for example, I happen to know about reinforcement learning. In reinforcement learning, you can, in imitation learning, which is a supervised fashion of reinforcement learning, you can also use GANs to train a supervised model instead of, train a model in an unsupervised manner as compared to train it in a supervised manner. So instead of training, mapping the input to the output to the labels directly, you try to make the generator generate a similar distribution as compared to the output label. Right. But in this case, you have label data, so you should be able to train. You should, or at least you have some label data for you to define metrics. However, other tasks such as the image generation that we saw earlier, that generating realistically looking images is not easily quantifiable, at least not quantifiable or programmatically, right? So there are here a few possible evaluation methods to evaluate those. I think the approximate test likelihood was removed because I think it's a bit, I would say it's overly complex. It's not really, and it's not really well used in practice because that requires the generation of a large amount of data to actually try to approximate your to approximate the distribution that is generated by the generator and compare whether that distribution is similar to your training data. So now let's look. So the obvious choice for evaluating whether the image is realistic or not is human evaluation. It's expensive, time-consuming, and non-reproducible. But it's probably the only justifiable way to say that the images are realistic. But however, with Amazon Mechanical Turk, which is a platform that you can hire random guys to help you label the data, it may not be so hard. However, the quality of the labeling is, well, let's say questionable. Yeah. Yeah. But so at least, some of them are trustable, but at least you have to do some data cleaning, and perhaps you need to pay multiple guys to label the same image, to make sure that so that you can choose. I guess you can do some kind of cleaning on the data and get a good label for a particular image, because otherwise some people may just randomly label the images, as opposed to actually doing the task. Right. And another choice would be to evaluate with a pre-trained discriminative network. For example, the concept of inception score. So we can use the inception V3 architecture and to classify the generated images. As Manish has mentioned, the inception network should produce a variety of labels. This is because GAN have a common mode of failure called mode collapse, where a generator only generates one or a few kinds of data as opposed to the entire test set, the distribution from the entire test set. So let's say if you are using an ImageNet, if you train a generator to generate images from the ImageNet, then the inception should be, then your discriminative network should be able to should be able to produce labels for all 1,000 classes, or at least most of them, yeah, and not just one or two classes out of the 1,000 classes of images. And so each label should have a high confidence or low entropy. That means your generated images should be classified as, well, some classes with determination, instead of being a more or less random images or an image of let's say two classes spliced together, so that the discriminated network will not be confident enough to classify the image as a single class. Yeah. Any questions on evaluation? All right, if not, that's the end of the lecture. Thank you so much for coming.